All right, let's take a moment to review molecular orbitals. And we'll take a look at them in the light of organic molecules. So first, let's take a look back to our atomic orbitals. If we remember, back in Gen Chem 1, we learned about 4 different orbital types that really talk about different shapes of what are mathematical models of electron probability. Remember that orbitals are not physical things, they are just maps of where we are likely to find an electron. And we saw that we had s orbitals, which were roughly spherical patterns, that had areas that the electron could be anywhere within that. P orbitals, on the other hand, had a node in the middle, where electrons could not exist at the node, but they could exist on either side. And electrons are allowed to pass through that node without ever actually existing in it. Remember, that's some weird stuff that you'll learn called tunneling. But electrons can actually pass through from one side of the p orbital to the other without ever actually crossing the node. So the node is just an energy barrier. It's not a real physical thing, neither is the orbital itself. But suffice it to say, the energy of having the electron there is so high that it can't possibly exist there. And so it can exist on either side. In d orbitals, we have 2 nodes, where electrons cannot exist in either of them, but the electron is able to move between all 4 lobes of the node, of the orbital, in either case. So we have nodes around here. And if we remember, when we talked about combining atomic orbitals into molecular orbitals, like we did for hydrogen, you know, we did something kind of like this. We had a 1s, we split it up, we had a sigma star and a sigma 1s. We had an electron each, and we had both of them in the bonding orbital, right? So this would be for each 2. The same idea is going to take place when we're talking about conjugated systems. Note that we had 1 electron from an s orbital, and we combined those to make a sigma orbital. We're going to see that when we're talking about bigger molecules, specifically conjugated systems, that we're going to end up with a number of molecular orbitals equal to the number of electrons we put in. For the hydrogen example, we end up with 2 orbitals, 2 molecular orbitals. We have a sigma orbital and a sigma star antibonding orbital. But we put in 2 electrons, we got 2 orbitals out. And we're going to see the same thing will be true for molecular orbitals. If we take a look at the molecular orbitals of butadiene, our absolute favorite diene, right? 1,3-butadiene. We're going to see that this is a 4-pi electron system. And we see that in that there are 2 double bonds that are conjugated together. Each double bond is 2 pi electrons. So 2 double bonds, therefore, would be 4 pi electrons. And if we have 4 pi electrons, we're going to end up with 4 different molecular orbitals for those electrons to reside in. And we're going to see that these would be similar, somewhat, to what we studied, but a bit more complicated, because they're not just a single molecular orbital, we have multiple. And we're going to see here that if we consider these, as I've already drawn them, with energy being the y-axis, we don't have an x-axis, this is just ranking them in terms of energy, we can see that there are nodes within these molecular orbitals as well. If we start with the lowest one, at a node, we're going to see the phases of the p orbitals switch. So if you remember, p orbitals have essentially a phase to them. This is just a mathematical ability of them to either combine constructively or to combine destructively. So if they are in phase, they will combine constructively. We could say that maybe two pluses put together, or as I've used colors. Or if a plus and minus come together, they will destructively interfere, thereby forming a node. And so, if we look at the lowest energy, the one at the very bottom here, we see there are 0 nodes in this orbital diagram. All of the purple ones are in phase with each other, all on the top. And all of the green ones are in phase with each other. We're going to see we have a node in the next molecular orbital, right in the middle. We have one node. At that node, we have the purple and green switching sides, because at that intersection is where they would destructively interfere, thereby forming that node. If we go up to our next orbital, these are just ways of arranging the phases. We see that we're going to have 2 nodes here that exist where we have the orbital switching phase. And then, of course, at the top one, we have a node at every one, and so we have 3 nodes there. If we wanted to consider what this looks like, the one we're most familiar with is the one node one, where we can see clearly we have a double bond and a double bond. I'm drawing it specifically this way to make it more analogous to the molecular orbital. We have 2 pi orbitals, 2p orbitals rather, overlapping to form a double bond. That's how double bonds are formed, right? P orbitals overlapping. And we see that happening on the other side. It doesn't matter if we use green or purple, by the way. I'm just using the purple ones just to make it more clear. But we see that where we have this node here preventing those 2 orbitals from combining into one. And that's how we normally view butadiene, as having this one node. The 0 node one actually looks just like one of our hybrid resonance models, where we have our 4 carbons, but they're all sharing the electrons equally. With no nodes, the electrons are freely dispersed throughout the entire molecule. So we have complete free movement of electrons. They're all just happily floating around. And we see that it's going to be our lowest energy state, where we have no barriers to the electron movement. With one node, we see that we have kind of 2 distinct double bonds. And interesting, though, if we look at the 2 nodes example, what that looks like is something that we might consider a resonance form of butadiene, where we have now a double bond in the middle, where those 2 purples can overlap with each other. But on either side, we have individual p orbitals. And we can consider this either as formal charges with a full lone pair, or we can have them as radicals. In either case, just a way of kind of showing how the electrons are dispersed. So in either case, we see that this is going to be less stable, right? We know that introducing radicals or formal charges into a molecule typically destabilizes it. And we see here that we have a double bond in the middle. That's allowing those 2 p orbitals to overlap so we can form that pi bond. But we have 2 p orbitals on the ends that are simply not available for us. They're going to be for double bonding, at least. We have either radicals or empty orbitals. And if we look at the 3-node system, we no longer have any double bonds. We have either radicals everywhere, or we have lone pairs and plus and minus everywhere. So either one of these. These are not quite representations, but these are ways of making it a little bit more, taking it from the theoretical side to maybe a little bit more practical. So we can see here that this one with 4 radicals is quite unstable. That's the highest energy state. And so if we have 4 pi electrons, and we made 4 different molecular orbitals, if we look back at our hydrogen example, we had 2 orbitals combining to make a sigma and a sigma star. We had 2 electrons. Those all were able to fit into our lowest energy orbital. We're going to see with a 4 pi system, I'm going to just draw them here, we're able to put our 4 electrons into the lowest 2 orbitals. And so we see here that we're putting them into orbitals that would have either 0 nodes or 1 nodes, the lowest 2 energy orbitals. And as we can imagine, as we go more and more up, that we start getting more and more unstable. We get less and less stable, either way. And we have names for these that we're going to talk about. Specifically, the 0 node orbital is so special, we typically don't see it doing a lot of things because it's very low energy. So it's already quite happy. But we can maybe get it to work sometimes. However, we usually see most of the chemistry happening at these 2 orbitals, where we have what's called the highest energy occupied, meaning there are electrons within it, molecular orbital, or it's abbreviated HOMO. Highest occupied molecular orbital, highest in terms of energy. So that's the highest energy orbital that all of our electrons happen to be in. And this one, the one that doesn't have any electron, is our lowest energy, unoccupied, no electrons are in it, molecular orbital, or LUMO. And so at any given molecule, that's specifically talking about conjugated systems, the orbitals of interest to us are the HOMO and LUMO. The HOMO is your highest occupied molecular orbital, and the LUMO is your lowest unoccupied molecular orbital. So if we're having an electron rich substance attacking another, we'll see it's the electrons from the HOMO that will be attacking the LUMO of another molecule. And we'll see that in our next video. But for now, suffice it to say that an orbital diagram like this shows you the arrangements of the orbitals in terms of their phases from low energy to high energy. Lowest energy always is 0 nodes, just like an s orbital has no nodes. And a p orbital will have 1 node, and a d orbital has 2. F orbitals have 3. And in butadiene, we see that we're going to have the same idea. 0 nodes, 1 node, 2 node, 3 nodes, all the way up to n-1. We had 4 pi electrons here, so we're going to have up to 3 nodes, n-1, 4 minus 1, 3. For hexatriene, which has 6 pi electrons, we'll have 6 different orbitals from 0 nodes to 5 nodes. And there's an example of that in your book that you can see. So with that, in our next video, we'll take a look at how HOMO and LUMO of different molecules can interact to make reactions happen.